Well, if you made it this far, we're hopefully on the last lecture here. The last lecture, as far as the topic is called psychopharmacology. And this, I think, is the most interesting of all the topics we actually have. In the field of psychopharmacology, what we actually try to do is we try to study how drugs that we take, drugs from outside the body, can actually impact our behavior. So a psychopharmacologist looks at how drugs affect behavior. Notice this is different than electrophysiology with how action potentials work. This is different than neurochemistry because we're not studying a specific chemical and how it's made, the neurotransmitters and released. Now we're studying how a drug, pharmacology, affects behavior. So psychopharmacology researchers, which is what I used to be, study what happens when you give drugs to animals or humans and the effect on behavior. Hopefully you can understand this is a huge field because now with humans there are all sorts of drugs that do all sorts of things. This particular field, though, is very much tied to the field of neurochemistry because when you take these drugs, they do certainly affect your behavior by affecting what? Neurotransmission, the process that we just described with how a neurotransmitter works and functions. So this is what drug companies do, and this is really one of the key points to this class is to get you kind of updated on how all of this works. And if you understand the electrophysiology, the neurochemistry, then this should kind of fit right in. So the first big issue here is the issue of reductionism. And in the issue of reductionism, remember that way back when in the first lecture with Descartes, are mind and body separate? Well, think about this question. Are mind and body separate or are they not? In this field, we basically decide not necessarily. We follow some form of monism. Maybe there's a relationship between mind and body. So now we've almost gotten into the age of what's called designer drugs. Have you heard this term before, designer drugs? Designer drugs, the idea is, can you actually make a drug that works so specifically that you can take that drug, it can go down to the neurotransmitter level, fix just one little part of the neurotransmission process, and thus fix one behavior and not cause all these side effects. So the issue of type reductionism is very important here. If you're a pharmaceutical company and you can create the perfect molecule, maybe you could just work at one type of receptor, one level, and then fix the behavior you want and not cause all these side effects. So this is a huge field, and I hope I can show you some of the ideas behind this. So let's start off with just some basics here. I hope you've heard the term agonist and antagonist before. In the field of psychopharmacology, when you take drugs, drugs can either be agonists, that is, they mimic the neurotransmitter, or they can be antagonists. They can block the neurotransmitter. So let me give you an example or two of this. Let's actually start with the example that works at the level of synthesis. We've already mentioned Parkinson's disease a few times. Unfortunately, my dad has this disease, which wrecks motor transmission. Remember, it works in the substantia nigra, and there's not enough dopamine. So the less dopamine you have up there, the more you're going to have these tremors and problems with motoric function. So what they do to treat Parkinson's disease is they give the molecule L-DOPA. I think it's called Sinemet. They give L-DOPA to people. It gets through the blood-brain barrier, and it's considered a dopamine agonist. It will mimic dopamine. It'll produce more dopamine. So when it's taken up, it's considered a dopamine agonist. It basically mimics dopamine. Another example of this, if you will, is not so much with the synthesis step that we talked about, but actually works at a slightly different level. There are neurotransmitters in your brain that are called endorphins. They're called endorphins. And that basically means endo, morphine, in your brain. And it turns out they didn't discover these naturally occurring pain molecules, or pleasure molecules, if you will, until long after they had a good drug for it. You know what the drug was? Morphine. When people take morphine, the idea is if you take morphine, it goes up to this little synaptic gap that has the endorphins in it, and it actually helps the endorphin bind better. So morphine is considered an endorphin agonist. but it's not working at the synthesis level, it's working at the postsynaptic binding level. So drugs change behavior, and obviously what does morphine do? It decreases pain because they work at a specific level of neurochemistry that then changes behavior. Wouldn't it be great if you could take a drug like morphine and actually create an even better molecule? What's the problem with morphine? Well, when you take morphine, yeah, it does help with the pain, but it has a lot of side effects. One of the reasons it has side effects is that it not only binds to the endorphins up there, but some other molecules as well. Which actually brings us kind of into the next issue a little bit. I'll probably get into this a little more in a few minutes, but it's the issue of receptor subtypes, and maybe this is a good place to do this. There's a handout there on opiate receptors. It's at the end of the handouts there in your thing. Let's see, it has, well, I hope it's in there. Yeah, it looks like it's the Bio at Davidson handout. Think about it for just a second. This issue of receptor subtypes. It turns out that when you have a product like endorphins and a product like morphine, there are 3 different types of receptors for the endorphins. And if you look at that handout, these 3 different receptors, they're given different names. One's called mu1, mu2, kappa, and delta. They all have slightly different shapes. And it turns out that endorphins will kind of bind to all of these. So it'll help with pain, but it'll also cause some side effects. Think of the advantage, if you're a drug company, if you could create a molecule that would just bind to one of them. Maybe what would happen is if you could create a molecule that just binds to one receptor subtype, you might be able to fix the behavior in question, pain, but not cause any side effects. So this is the issue of receptor subtypes. They've actually identified for different types of neurotransmitters all these different types of receptor subtypes. They're different shapes, different morphology. And the idea might be that if we can fix one little receptor, we might fix the problem behavior and not cause side effects. So there's a lot of research going on with this issue of receptor subtypes. So that is one particular issue I wanted to mention to you here today. Let me give you some other examples of psychopharmacology. Let's deal with depression. So depression, the first types of products that were out there with depression. If you turn to page 132 of your book, the first products were called MAO inhibitors. Let me try to explain this to you. MAOs, they're called monoamine oxidase inhibitors. It turns out that depression seems to be related to low levels of the catecholamines and serotonin. And if you look at the picture of at least the catecholamines, you can see that monoamine oxidase destroys dopamine and norepinephrine and actually serotonin to a degree. And so the first line of drugs that was used to treat depression were monoamine oxidase inhibitors. If you don't destroy dopamine, norepinephrine, and serotonin, if they're there in the synaptic gap more, that's higher levels, maybe less depression. And that did work. But there were problems with the monoamine oxidase inhibitors. The monoamine oxidase inhibitors, if you look at any medicine that you take, even now, they had a lot of interactions. They interacted with alcohol, they interacted with cheese, with wine, with all these different things. So they were very non-specific. So yes, they helped depression, but they were working on so many different neurotransmitters that there were a lot of side effects. What do we use now? Well, we use SSRIs, Zoloft, Paxil. And what's the other one? Zoloft, Paxil, and Prozac, of course. That when these came out in the 80s, they actually found that when you give these products, they are called SSRIs, selective serotonin reuptake inhibitors. They block the reuptake of serotonin. So serotonin can't be taken back up. That means there's more serotonin in the synapse. So these products are considered serotonin agonists because they increase serotonin levels and thus help depression. They are more specific than the MAO inhibitors, although there's still some side effects even associated with them. So this is an example of how products have gotten better, and now we have these SSRIs and other drugs as well. The products like Prozac, Paxil, and Zoloft are considered serotonin agonists because they block the reuptake of serotonin. That means serotonin stays in the synapse and basically works better. So we have that one. Let me flip you over to a few other pages here. If you turn to page 157 of your book, just a few other examples. If you take a product, what should we have here? As it says, morphine. If you look on 157, as we said, morphine is considered an endorphin agonist, and so is alcohol, endorphin and actually GABA agonist as well. You can go down the list here just a little bit. Xanax, can you see Xanax there? Xanax is considered a GABA agonist. Remember, it opens up a chloride channel and causes IPSPs. You can see amphetamines. Amphetamines are going to increase dopamine release, so it'll actually increase the release of dopamine presynaptically, and so much dopamine gets released in norepinephrine that it's going to cause behavioral activation. So you can see a couple of examples there. Nicotine stimulates acetylcholine receptors, and so that's another example as well. And finally, in the very back of the book, where was I? They actually have some examples, I think it's in the psychoactive chapter with depression and schizophrenia. One of the main drugs used to treat schizophrenia is the drug Haldol or clozapine. How do they work? Well, it's believed that schizophrenia is linked to having too much dopamine binding postsynaptically. So these products, Haldol and clozapine, basically block the dopamine receptor. So, hopefully this makes sense. I've got one little last recording here that I'll play, and then we'll be done with this.